All right, everybody, 10:15. Go ahead and get started here. Well, we're going to start by talking about the math review and answering as many relevant questions to the course as possible. A lot of you did have really good questions about the course and about the material already. We'll go through a couple of the problems from the math review, and then we'll start getting into some new material talking about how do we measure things. It turns out, like everything in sciences, we have a procedure for measuring things. It's not as simple as, what do you mean? You just measure it. We actually have a process that we go through to make sure we write down the right number of digits. And so that's what we're going to work on today. And how do we know where to round when we actually do some math with things? I also want to stress before we get into that, for the math review, I'm not going to be grading on significant figures or rounding, because I gave you that math review just to make sure you know how to do the math. So I want you to just think about it like math, not necessarily worrying about where to round things. If you've already had that in a previous class and you weren't sure, you didn't remember the rules for where to round, don't worry about it for this first assignment. Worry about it from here forward. But don't, and if you already submitted the math review and then you see this stuff and like, oh shoot, I did all that wrong, don't go back and resubmit it. You can, I guess, if you really want to, but I'm not going to grade you on that. So don't panic about it. There we go. First off, recap from last, what the one thing from last lecture that's going to be on the final. What's the difference between a scientific law and scientific theory? Anybody want to take a stab? Corbin?
Scientific law describes what, and scientific theory describes how.
How or why?
How or why, okay.
Yeah, so theory, they can both be just as supported by evidence. That's the main point I'm trying to get over, is everybody's used to the word theory meaning something that's not concrete. Nothing in science is really concrete, but just because it's a theory doesn't mean it's less well supported. It means it can be just as strong as a scientific law in terms of how much evidence we have for it. The difference is what those two things do. If it's just describing what's going to happen, it's a law. If it's going to describe why something happens, it's a theory. That's the only difference between those two things. And once again, that will be 2 out of the 100 points on your final exam. Only 2 points, but they add up. There's a few other things that I'll tell you when we get to them that I will guarantee you this will be on the final exam. This is your first one. All right. And I would really, really like it if I could give everybody those 2 points. If everybody got this answer correct. That almost never happens. There's usually a few points where I'm there, 48 out of 50 people are going to get these questions right. I really want it to be the 50 out of 50, but it never happens. So let's make this the year that everybody gets this question right. So just to, as our icebreaker, get us thinking about things. I picked a couple of random quiz questions. Somebody asked about their favorite scary movie. I'm old school when it comes to scary movies. I like John Carpenter's The Thing, and I like Alien. My favorite scary movies. If we're going in the last decade, I'd say Get Out. I think Get Out is a fantastic movie. One of my favorites. I actually watched Alien with my. He's now 11, but we watched it when he was 9, and it became his favorite movie for a couple months, which was a lot of fun. I did my job right, so he's my oldest, and he now is obsessed with Alien and Predator movies. So it's been fun. I get to watch movies that I like to watch because I got him into it. So a lot of people ask why I'm a professor. I think I covered that a little bit the other day. I like talking about science. When did I realize I wanted to be a professor? In high school, I kind of thought I wanted to just be a high school teacher because my high school chem teacher was really cool. Then I went to college and this is kind of fun. Maybe I'll go to grad school just to see how hard it is. And it turns out it's really hard. Not in the it's really, really hard to understand the material. It was that also, but it's also kind of a marathon where in science and STEM in general, you go to grad school and a PhD program, it's There are unreasonable toxic expectations from most research groups. So it was a lot of working 60, 70, 80 hours a week for less than minimum wage. And then being told that what you're doing isn't good enough or you're not trying hard enough. That was just my experience. There are other research groups that are less toxic. But that's when I realized when I was a TA for a upper division class that was in my research area. I basically taught the whole class, and it was really, really fun. And I realized I was having way more fun on the days when I got to teach that class and get to have office hours and talk to the students about what they were learning. That was a lot more fun for me than actually doing the research. So part of it was that I realized I like the idea of research, and I have a ton of respect for people that can do research and live in that world, but that's not for me. So I left to become an instructor so that I could talk about science, get you all excited about science without actually having to do the science myself, because it's really, really high pressure, high stress environment, and that's not what I really wanted. I would also, at the second part here, a lot of people are not interested, or I really hate kids these days type arguments. I don't think that there's anything wrong with modern generations of modern technology. I think it's being used maybe irresponsibly by corporations, things like that. I would just say that if you get really good at something that's not on your phone, pick something, make it a hobby, make it something you study for your profession, but get good at something and be excited about something that's not on the internet. And I say that as somebody who loves spending time on the internet. But you also have to balance that out with other things. And if you can do that, and you think, I saw a good term for this the other day in a psychology paper. Intellectual grit is what they call being able to think about something difficult for an extended period of time without giving up or without going on to something else. I think that's, as AI takes over more and more of the everyday tasks, being able to actually sit down with something you don't fully understand and think about it until you do fully understand it is going to become a more and more rare skill. So if I could tell you to take anything away from this class, it's get good at that. Get good at sitting and thinking with things, even if you're not comfortable with it, even if the assignment's hard, without just immediately going to the key or immediately going to AI or immediately going to somebody else. Is going to be something that I think is going to serve you well if you can do that. That said, I'm not entirely immune to that. I don't use AI for things, but I do get frustrated with things that I don't really want to be doing, that I don't think are relevant to the things that I like. I understand that, but anyway, that's enough about that. Favorite artists or bands to listen to? I listen to a little bit of everything. I'm going through a pretty strong Neil Young phase right now, but I really like a lot of more. I really like a lot of modern country, some of the alt country stuff. Jason Isbell's one of my favorites. Sturgill Simpson's one of my favorites. There's like a really, really strong alt country, independent country community. Has a lot of really interesting sounds going on. But I fluctuate, I go in and out. Sometimes, I think my Spotify Wrapped last year said that in this late spring, I listened to a lot of, what did they call it? Cyberpunk hip hop, I guess is what they call Run the Jewels. I listened to a lot of Run the Jewels and Death Grips and stuff like that too. So I'm kind of all over the place. If I choose a different career path, what would be? I think aerospace engineering would be a lot of fun. It's a really, really cool problem solving. What can you expect to see from me as a teacher? I stand up and talk. There's a lot of material we have to get through in this class, and unfortunately, I don't have a good way to, that's not just lecture based in terms of getting through the material we have to get through in this class. And so it's going to be a lot of, I want it to be a dialogue. I want you to stop me, ask questions while I'm standing up here talking, but basically I lecture. And then we get our active learning part, and the more interactive part's going to be in labs. So you get 3 hours a week is going to be in labs where we're actually going through material when it's more not necessarily one-on-one, but I go around all the groups and check in. But then when we're getting to lecture, it's kind of lecture. which I get is not always the most fun, but I'll try to make it entertaining at least. Somebody asked about my daughter's basketball game. Her game, I want to say she's only in fourth grade. And so the way that they do the Kale Basketball League over in Kale is third, fourth, and fifth grade girls are all on the same team. So there's a really wide range. I don't know if you've seen a third grader versus a fifth grader. And they hadn't even had a practice before their first game. So I think the final score was 8-6, but I think she won. My older son had a double header the following night, and he won both games. He was pretty pleased about that. So thanks for asking. Along with those, if you just head off the next question, I have 3 kids. I have 11, 9, and 3. And the 3-year-old is a real bear these days. All right, relevant course questions. The other thing I take away from all these questions is I like when you all ask these questions because I can kind of tell how well I'm going over the material based on how many questions are about stuff like the course or the material versus how many things are random questions. And you all apparently are a little bit concerned about the structure of the class because I have 2 full pages, and this isn't even all of them, of course related questions to the structure of the course. So I'm going to try and calm everybody down about that a little bit. You don't have an attendance piece. I'm not going to take attendance. I record the lectures so that if you're here, you can go back and rewatch them later. But if you do need to miss for some reason, you can watch the lecture recordings as well. It's just kind of on your own honor system. Like, don't fall behind. If you fall behind in this class, we move real fast and it's going to be hard to catch up. It's not impossible, but it's best to be here as much as you can, especially for the labs. The labs, I guess if you could say that there's a required attendance piece for this class, it's the labs. Because you can't really get the experience of being in the lab, mixing things up, measuring things yourself and doing without actually being there. And that is part of what this class is the hands-on experience. So that part is required attendance. But I'm not gonna like sit down and mark who was there or not. It's just gonna be based on, when you turn in your assignment, right? So it's not a separate category or anything. If you have a hard time remembering things that was just learned, do I have any tips? How do we overcome challenges? A lot of people had similar questions along those lines. Repetition and time is really the best thing I can tell you. It's going to be a lot of time. There's a few in-class quizzes that are closed book that are going to be sort of rote memorization. Basically, I'm going to make you memorize the periodic table names and symbols, not the numbers, not even where it is on the periodic table. But I'm going to give you a quiz where if I write Cl, you have to write chlorine. And if I write argon, you have to write Ar. Basically, just to make sure that there's sort of fluency in terms of switching back and forth between the symbols, which are the 2 letters, and then the names, which is the full name. There's really no way of getting around that other than just making you memorize it. There's some tips that I have when we get closer to that. Basically, it turns out a lot of the trickier ones to memorize actually have good stories associated with why is silver Ag instead of Si or something like that. Does anybody know why silver is Ag? Any guesses? Latin. What is silver in Latin? Anybody know? Argentum. So argentum is where the Ag comes from in silver. And same for a lot of the classical elements like gold is Au because in Latin it's aurum. There's also some other ones. One of the fun ones is W is the symbol. Anybody know what W is on the periodic table? It's tungsten, which is a weird, it doesn't seem like there's much of a connection there, right? At all. The story that I've heard, that I've read about is that 2 different research groups discovered tungsten at roughly the same time in I want to say it was the 1800s. And they couldn't prove who discovered it first. And so as a compromise, the way that it works is if you discover a new element, you get to name the element typically, or you get to suggest a name and then it's voted on, and usually they accept what your research group proposes. In this case, since they couldn't decide who discovered it first, they let one group decide the name and the other group got to pick the symbol. And the British group named it tungsten, and the German group wanted to call it wolfram. And so wolfram is where the W comes from, but the British group named it tungsten after a person probably. So there's lots of little stories like that. If you know, like that would be a really hard one to remember otherwise, right? And so some of it is going to be, I've got some tips and stories and way to memorize things, stuff like that. In general though, when it comes to how do we retain these things, it's just going to be repetition. That's part of what those quizzes every week are for. It's part of what we're going to try and keep the lab assignments, relevant to the course material. So we're going to talk about measurements today in here, and then we're going to go to lab and you're going to measure stuff. So we're going to get some practice here, then you're going to go do it, and then you're going to do the lab write-up and answer the questions about it. And after you've seen it 3 times, done it yourself twice, and then see it again on a quiz, you've got a decent chance of retaining it. That's kind of why the course is structured the way it is to give you as much of that repetition and scaffolding as possible. Somebody asked about, does lab actually go full time? Plan on it going full time usually. It won't. Hardly ever will you actually need to spend the whole 3 hours in lab, but you want to allow for it because there are a few procedures that are just longer. And there are some times when it's going to take your particular group might take longer in some cases. If you did something wrong at the beginning and then you realize that all your numbers don't make any sense and have to go back and redo that first part for your later numbers to make any sense. There's little stuff like that can make it so it's not always going to be the same group as there to the very end. Some groups do tend to go slower than others, and that's fine. But some groups typically are done pretty fast. I won't commit to a time because it varies widely depending on what week it is and what lab we're doing. But you very rarely will you actually go a full 3 hours in lab. It'll mostly, at the very least, you'll finish getting your data, then you can go get food or something and come back and do part of the lab write-up. You don't have to finish the lab write-up before you leave. So there's some flexibility there. If you have other commitments, like, hey, my work schedule changed this week and I need to leave by 3:45 to make it to work on time. If it's not an everyday thing, if it's not an every week thing, then we can usually make that work. And I'll just say, okay, well, your lab's going to finish, your partners are going to finish getting the data, get the rest of the data from them. And it'll be maybe a point deduction because you weren't there for the entire procedure. But we'll try to be as flexible as possible because I know things come up. And that's reasonable. Somebody else asked about, are we going to need to pay full attention 24/7? And then start asking about online classes. This is not designed to be an online class. COVID was really rough for chemistry students because chemistry is not easy to learn in an online environment, especially when you factor in the lab piece. So it's not an online class for a reason. We really don't even offer online classes in chemistry because we have that lab component. Every class we have has a lab component. Is it going to need full attention 24/7? No, I try to be respectful to some extent of the fact that there are other classes. None of them are as important as my class, obviously. But I know that you all are taking other classes, have family commitments, have work, have other stuff, and ideally have a hobby or two along, when it is winter, so the snow's getting nice. So no, you don't need to pay attention 24/7, but it's going to require hours. It's going to require time. So just keep putting in the effort to get the assignments done. Come ask questions when you have questions, things like that, and it'll be okay. Is there support in lean? I do a lot of partial credit for grading. In general, I don't want to have to give you zeros for missing assignments. So if you got 2/3 of an assignment done and the due date's today, and you well, I really don't want to turn it in until I finish it, that's okay, but it's really easy to let that pile up and then zeros start piling. So a lot of times it's actually better to turn in an assignment 2/3 the way done. You'll get dinged some points, but at least you've got some points there. and you're not sitting on a 0, because those zeros are really, really hard to overcome. So get something turned in, and I give you as much credit as I can, right? The hope is, if you have assignments 2/3 of the way done, and you really want to finish, or you need to ask about those last 2 things, turning it in late's okay. I'm pretty lenient with turning stuff in late, but don't let it turn into a snowball. And don't let it stay a 0, because you have this assignment that's already late, now you just don't think about it anymore, and now it starts weighing on your mind, and you just bury it. Don't go down that route. I see students every year do that, and that's a problem. And that gets really hard to come back from really quickly. Okay. Group projects, I mentioned lab. Lab is in groups. It's not safe, especially as a beginning student, to work on a lab on your own. Basically, you need 2 sets of eyes, 2 pairs of hands, to make sure that you're not doing anything dumb, that you're reading the procedure properly. Sometimes you just physically need 4 hands to be able to hold everything in place. So yes, you will be working, but that's the extent of the group projects. Beyond that, all of the homework, all of the quizzes, everything else is going to be, you can do it on your own, or you can work in groups, whatever you prefer. But labs, you have to work in groups. And as you get into 3rd, 4th year college chemistry classes, that's when you start being allowed to work individually in lab. But even then, you still have to have somebody who knows where you are, because the last thing you want to do is spill some diethyl ether and knock yourself out, and then wake up on the floor and nobody even knows you're there, right? So you still always want to be able to tell somebody, hey, I'm working in lab these hours, so that they know where you are. If they haven't seen you in a couple hours, they might come check on you, right? But you all don't need to worry about that yet, because you'll all be in groups for now. And then just to reiterate, no textbook. The reading material is all linked in Canvas. And the lab procedures and report sheets and everything are going to be provided for you in lab. So you don't need to buy anything else for this class. All right, did any of these bring up other questions anybody has? Because there's more. I will not spend this much time answering quiz questions. I'll spend most of the time answering them when I grade your quizzes, but in this case, because these are course related and I want to make sure everybody sees them, I'm taking extra time for this class. Can you turn in an assignment of random paper, or if you need to print it out? Random paper is fine. I don't mind that at all. In fact, if you're comfortable working from a computer screen and just using binder paper, perfect. That's great. That'll save us some paper. And that's true for every class, for every assignment. It's convenient to use the lab reports, just because everything's already written out for you, but you don't have to. If you don't have a copy or something like that, you can always turn it in on random paper. If you've never taken a chemistry class, great. This is not a class that requires you to have had chemistry before. If you had high school chemistry, then a lot of this is going to be review. Maybe it should be at a deeper level, higher expectations and faster than high school chemistry, but it's a lot of the same stuff. So that's totally fine if you haven't had that. If you are jumping right into Gen Chem has this class listed as a prereq, but even that is kind of stretching it. If you're strong at math, or if you feel like you're a strong student, or if you had high school chemistry, you can jump right into Gen Chem, which is the year-long sequence that starts in the fall. But it'll obviously, if you've seen the material before, it's easier to relearn something than it is to learn it for the first time, which is one of the reasons this class is a prereq for Gen Chem. But it's not going to be prohibitive to you passing this class if you haven't had chemistry before. That's fine. We'll talk about dangerous labs when we get into labs. We're talking about lab safety today too. This is a good question if you want to. What are different jobs or careers? There's a lot of science related jobs and careers that people don't think about. Do you know that science policy advisor is actually a career path? You can actually just get a job, get a science degree, and then get a job working for a politician, is basically be their advisor, so that when new things happen, in the world of science, your job is to learn them and then teach it to the politician and help form what their opinion is on what the government's role should be. That's actually a science-related career path. That's kind of cool that people don't think about that. Nobody thinks when they're 18, I want to be a science policy advisor. But maybe they should, because we could use more science education, scientifically literate people working in government. So there are a lot of different jobs and careers. I'm gonna focus on, or touch on some of them when we get to relevant material. When it comes to active conservation, you'll see a lot of that information if you guys start taking more environmental science classes. For instance, Scott Valentine is working on a project right now. He's our geology instructor to restore the meadow to the way that it was before Europeans got to Tahoe Valley. Our meadow is being slowly taken over by trees, which sounds great. Everybody loves trees, right? Except we actually need wetlands to filter water before it makes it to the lake to keep our basin as a whole healthy. We actually want wetlands. We don't want more forest. We have plenty of forest. So that project is actually all about, let's go in and cut down as many trees and get rid of as many trees as possible in the meadow to try and restore it to the state that it was in. So there's a lot of people work for the Department of Natural Resources and things like that, but there's also a lot of different ways that you can participate in conservation outside of working directly for the DNR. As well, what's a good way to incorporate chemistry mindset in everyday life? Think about it. The more you spend time with it, the more it's going to slowly take over everything. You've seen that, I'm sure, anytime you get obsessed with a particular type of music or a particular movie, you start seeing references to it in more places. The more you think about stuff, the more you'll start to incorporate it and the more you'll see the connections. So again, it all comes back to time and repetition. The more you think about it, the more you'll see it. Do I expect you to have a deep understanding of all aspects of chemistry to get through this class? Absolutely not. This is an intro level class. Even the full year-long Gen Chem series, it's 3 whole quarters, 36 weeks of mostly the same material that we're going to cover in this class. Every single chapter in Gen Chem is its own field of study or its own upper division chemistry course. So no, you are not going to be a chemistry expert when you come out of this class. Hopefully you understand a few aspects of chemistry and how it applies to things that you're going to study in the future, and you're set up to continue taking science classes, but that's not what this class is. This class is to get you just a bare, I don't want to say bare minimum, but just a real bare bones understanding of basic chemistry ideas that then can be fleshed out later as you take more science classes. And so no, you will not be an expert by the end of this class. You might have some aspect of it that you feel really good at and that you dig into more, hopefully. But don't panic. I'm not gonna replace 4 years of undergrad plus 4 years of grad school with one 12-week class, right? Last thing, work-life balance when it comes to heavy science workloads. If you're taking lots of science classes, science majors just work hard. STEM majors, allied health majors, there's perhaps an unreasonable level of comparison between STEM majors and comparative literature. Nothing against comparative literature. I love comparative literature. However, the workload is not the same. It's hard. I'm not saying that to scare you, but just to be realistic, that's one of the reasons why STEM degrees are so highly valued. When you get hired with a STEM degree, it's not necessarily because of all your knowledge. It's because you're demonstrating that 1, you know how to learn, and 2, you know how to work. If you have those 2 things, then you can get hired for a lot of different jobs. My partner has a biology degree and she works in human resources here on campus. She has a biology degree, not because that's related to human resources, because she was interested in biology. She was pre-med for the first 2 years of college. But because she had that science degree, that set her apart when she was applying for that job, because it showed she knows how to learn, she knows how to work. So that's. When it comes to feeling nervous, that's fair to feel nervous about it. You're gonna have to work hard, but that's also part of the payoff, is that you learn how to work hard. And then but it is a balancing act, I acknowledge that, and you're gonna have struggle with it sometimes. I struggle with it as well. All right, any other course related questions, course structure? Yeah.
So I know a bunch of us are also in Caroline's A&P class.
Yes.
We need to work together to make sure that we don't have like tests on the same day.
So for this class, we only have the one test.
Okay.
So it's just during finals week. Partly because we don't have time. I'll give in before that test, I'll give you a practice final a week ahead of time. That'll have the exact structure of the test. So it'll be the exact same test, just with different chemicals and different numbers. So finals week is gonna be hard because you've got to balance all your classes. If there's ever anything in particular where like, hey, we have A&P midterm this week, and we have 3 things due this week for chemistry as well, do you think that we could get an extension, or could we push the due date? Worst I can do is say no. It'll depend on the material, but usually I'm pretty generous with that. Probably in that case, what I would do is just push the deadline for the entire class if there's a bunch of stuff going on campus. But yeah, always ask. Anything else? Relevant stuff, finally. Somebody asked to go over part 3, part 4, and then part 5. I'll tackle this middle one first though. Scientific notation, we're gonna go over scientific, we're gonna use that all the time. You're gonna get very good at scientific notation, because that is the best way to represent both big numbers and small numbers, and we deal with a lot of those in chemistry. So the scientific notation is not something that, oh, I didn't get it on the math review, but I'm just gonna take the hit on the math review and then hope it doesn't come back. That's not gonna help. You're gonna need to get good at scientific notation. The good news is we're gonna keep working on it, get more and more practice with it. Just so we're all using the same terminology when it comes to scientific notation. When we're talking about scientific notation, this number here, that's called the coefficient. Basically, coefficient is what are the digits? And then the times 10 to this is called the power. The power is just where the decimal point is, right? So there's no math involved in going from regular standard notation to scientific notation. It's 2 ways of writing the same number. So if I wrote 0, 0, 0, 0, 0, 7, 0, 1. That is 1.07 times 10 to the 8. We'll talk about units more as soon as we're done with this part. This is the same number. There's no math involved going back and forth. It's just a different way of writing the same thing. It seems like there's a procedure. There's math that you have to do, but no, it's just another way of writing the same number. Right, so a couple of tips for scientific notation. How do you know if this is supposed to be a positive or a negative? Anybody have a good way of thinking about that? If it's a minus sign, what does that mean? It's going the other way. It's a minus sign. Basically, the way that I always think about it is 10 to the 8 is a big number, right? I'm taking a number in the ones place, and I'm going to multiply by a really, really big number. So the other way of writing it is a really, really big number. If you have a negative exponent, that's a 10 to the minus 4 is a small number. So whatever the rest of this is, I know that the overall thing is going to be a small number, right? So in this case, 0.00052 is the same number, right? So The easiest thing to get messed up with this, is it supposed to be a big number or small number? Just think about in standard notation, is it a small number? If it's a small number in standard notation, it's gonna have to have a negative exponent. Because that's what makes this 10 really small. Make sense? All right, so again, we're gonna do a lot of practice with scientific notation. We're gonna keep using scientific notation for the entire class. Use it a lot. Any other scientific notation questions?
I have one.
Yeah.
I kind of had a theory when I was reading it that is scientific notation named that you created as a means of maintaining the number of significant digits?
Yeah.
Okay.
So basically, so how do we know where to round? It's going to be based on how many digits we want to keep, how precise our measurement was. When you start doing math with these numbers, you're not sure where to round. Counting how many numbers are measured becomes a big deal. That's what we call significant figures or significant digits. Scientific notation is a really convenient way of specifying how many numbers were measured. How do I know that these are all going to be zeros? They might not be, and the true value for this distance might not be all zeros, but we only measured 3 digits. We only measured these first 3 digits. So we only write them, and then all these other zeros, they're just gonna like, it's kind of like, well, they average out to 0. We only care about it to the million centimeters. We don't care about the rest of these digits. We write them as zeros just so we know where to put the decimal point, but they're not actually going to be measured, right? And so scientific notation is a good way of conveying that. I don't need to worry about how many of these zeros are measured or not if I write it in scientific notation, because I'm very specifically saying these 3 digits were measured and the rest of it's not. More to come on measured numbers though, but that's exactly right. All right, it was, I just alt tabbed over. Part 3, part 4. All right. More scientific notation tips. There's a couple of really helpful things when it comes to doing math with scientific notation. One is partly, this is probably the most universal thing, is what I call a reasonableness check. Basically, before you hit enter on your calculator, you should have a halfway decent idea, at least is your number going to be a small number or a big number when it comes out. I'm not asking you to do this math in your head. You might get to the point where you can do some of these steps in your head, get pretty close to the real value. But at the very least, we've got big numbers on top. Do that one. No, there we go. We've got big numbers on top, but an even bigger number on bottom, 10 to the 22 on bottom. And even though these are really big numbers, 10 to the 15 is still a really big number. That's in the trillions. This is 10 to the 22. That's like a billion trillion. So with that in mind, before we do any of the math, we should know that should our answer be greater than 1 or less than 1? Well, the final answer for this whole thing should be a lot less than 1, because it's just a fraction, right? If you've got a big number on top and an even bigger number on bottom, like if I said, I don't know, 99 over 121. All a fraction is looking at that ratio, right? This number is 99 is a big number, 121 is even bigger. So without even doing anything, I know that this number is less than 1. Right? Apply that same logic to scientific notation. So that way, that's going to save you if you enter something on your calculator wrong. If you try to plug this into your calculator and you get a number that's bigger than 1, that should be a red flag, right? That should tell you I messed something up somewhere. And so those reasonableness checks, have at least an idea of what the answer is before you hit enter, is really, really helpful. When it comes to, without knowing the person who wrote that problem or that question asking to go through this, almost 100% what happened is if you try to just write this into your calculator, you're going to get a problem with the order of operations because it's not really shown. But it's implied when you have fractions that have multiplication, or sorry, that have subtraction or addition, that there's a set of parentheses there. If you don't put this top piece in parentheses, what will happen is you're going to, if you type that in, type in 1.15 times 10 to the 15 minus 2.5 times 10 to the 14 and then over 4.45 times 10 to the 22. If you just write it like that in your calculator doesn't know there's supposed to be parentheses, and so it's going to take this number, divide by 10 to the 22. So you're going to get something really small, and then it's going to subtract that from the 10 to the 15 number. So you're going to get something that's still in the 10 to the 15s range. So a big number when it should be a small number. Right, so if on your calculator you do that, you're fine. Because the parentheses are telling calculator to do the subtraction first and then do the division. And so pay attention to your parentheses. If you're not sure if it needs parentheses, having extra parentheses can't hurt. Having extra parentheses will never give you the wrong answer as long as you put them in the right spot. Missing parentheses will oftentimes give you the wrong answer. Also, spare or another tip, this caret symbol is really critical because what does that mean? To the power of. It basically means make it an exponent. So anytime you don't need the square button on your calculator anymore, as long as you know that. Because that's going to be how we raise things to powers that aren't just squaring it or to the third power. Right? The other time-saving shorthand that gets used for scientific notation is a capital E. If you look at most Texas Instruments TIs, they have a button that is just two capital E's. It's usually, you might have to hit the second function to get to it. That button is for scientific notation specifically. If you write 1.15 and then you hit that E button, it just gives you a capital E. That capital E means scientific notation. It means times 10 to the. So 1.15 times 10 to the 15. That is this number. That can be save you a lot of time and also help with the parentheses because it knows that this all goes together. It's all built into the programming. And you can do that in search engines too. If you use Google as a calculator, you type in an E in the middle of a number like this, it knows to treat that as scientific notation. And so that can be helpful too. The more comfortable you get with that, the faster it is to type these things in. For now, if you're not comfortable with that, you can just type in times 10 to the 15. It's not a bad idea to use lots of parentheses though, so that you don't wind up doing something like, let's see, 1.15 times 10 caret 15 over 10 caret 12. That's kind of ambiguously written. Because do I take that 15 and do I divide 15 by 10 to the 12? Or do I take this whole number and divide by 10 to the 12? It's not clearly written, right? So when in doubt, use those parentheses so that you can say, this is a whole number. And I'm going to take this whole number and divide by 10 to the 12. Because if I put that second. I don't have a way to, this is why I don't like this particular one. If I put the parentheses here instead, ignore this first parentheses. Or if I put it like that, now I'm specifically saying 15 divided by 10 to the 12 is the exponent for this first one. And so you can, using the parentheses as a way to force it to do the math in the order you want it to, right? So just be careful with that. All right. So any other questions about this part? Doing math with scientific notation. Reasonableness checks in parentheses are going to be your good friends when it comes to these problems. All right, and I'll also reiterate for this one. It says solve the equations for x in terms of y. Solve for x means get x by itself, right? In terms of y means you're not going to get a numerical answer at the end. Your answer when you solve for x is going to have y in it. And that's fine. That's what this problem is asking you to do. So then it's just all about remembering your steps. How do you do the algebra in the right order? Right? We're going to want to divide by 9 at some point to get this x by itself. But we can't do that until we take care of this piece first. So we start by subtracting 32y from both sides. Right, so if you need help on the order of algebra, I'm going to refer you to the math tutors over in the library. They're there all the time. Most of them have also taken chemistry. So they've seen both this assignment specifically, but also a lot of the same applications and can help you. If you need help on, I don't remember how to do this algebra, talk to me in a smaller setting. In lab, or just come to my office hours and I'll help you work through it, or go to the tutors and they might have some tips for reminding you how to do it in the right order. But all I want to say about this one is it's all just about remembering the right order to do these steps in, right? And I'm not a math teacher. I teach a lot of math and I can help you with things. But my specialty is not in helping people learn algebra for the first time, so I'm rusty on that. It's been a long time since I remembered the right order how to do, since I first learned how to do problems like this. So I can help you, but the tutors might have learned it more recently or might have some other tips for, oh, here's how you remember what order to do this stuff in. I don't want to say don't ask me because I'm happy to help you with that, but it's been a bit since I learned that. So it's kind of second nature. This one. What do we have to do first for this bottom one?
Move the y plus 4 to the 17 side.
Yeah, we have these parentheses. We can't do anything to get x by itself as long as it's still part of a fraction. We can't do anything about this x minus 5 until we get rid of everything else around it. One of the ways you can think about this particular one is if you remember the 17 over 1, that over 1 is always there, right? So you could do, does anybody else learn how to do, called it cross multiplication or the butterfly rule or things like that? You can't just do a butterfly rule for this one. You just have to remember that 17 over 1. When you multiply both sides by 1, that doesn't change anything on this side. So the other way you can think about it is I'm just multiplying both sides by y plus 4. Then you get 17 times y plus 4. Equals 1.5 x minus 5. Then you can divide both sides by 1.5. Those cancel out. You can do 17 over 1.5 and then distribute in there. That's not wrong. You don't need to answer this question. This question says solve for x, which just means get x by itself, which means you don't have to simplify the other side. A lot of times in the sciences, it's helpful to leave things unsimplified so you can see where the numbers came from. Sometimes it's helpful to simplify things. I'm not gonna be picky about what format it's in. If you can get X by itself, that's all you need to do. Right, and then once we do that, now we're just down to X minus 5, so then we get something like X equals 17 over 1.5 times Y plus 4 whole thing plus 5. That looks a little clunky, but that's a complete answer. You wanted to simplify it a little bit, maybe at least do this, maybe do this and distribute it so that you can combine all of your numbers that don't have variables. That's great too. That's good practice. This is a full credit answer as it is written right here. Right? I just said solve for X. X is 17 over 1.5 times parentheses Y plus 4 close parentheses plus 5. It's a mouthful, but it's right. That's fine. All right. Any other questions on these ones? Feeling okay about math review? Down here. This is just, there's no addition, subtraction. This is easy algebra. It's all just multiplication, division. Just not using X's and Y's. All your regular rules still apply when it comes to moving variables around. So if we start with PV equals nRT, we want to get R by itself. We just divide both sides by NT. N cancels out, the T cancels out, we get R equals PV equals over R equals PV over NT. Does it matter what those variables are? Not in the slightest. If I really wanted to make it look confusing without changing anything, I could have used Greek letters. Then they'd look really wonky, but there's absolutely nothing wrong with that. We wanted to do this as pi times V equals sigma R tau. I don't remember how you signify the difference between a tau, capital tau, and a T. They look the same. Doesn't really matter what the variables are, right? Divide both sides by sigma, divide both sides by tau. You're still gonna get R by itself the same way. Okay, so don't be thrown off just because it's not X's and Y's. Questions? All right. We're now 55 minutes into lecture and we haven't touched any new material. That's totally normal for these classes because I want you to be able to see the material twice. And so sometimes that means we review for the first half of class before we get to new material the second half of class. Let me see if this is a good place to take a break or if I want to go over a couple things first. Let's take our break. Take our break here, come back at 11:20. And we'll start talking more about units and numbers. So that means that I was getting that she was a student. So you can see it, you can't participate.
Oh, okay, no problem. I was just making sure.
Yeah, no, I'm hopeful we'll have some resources for this, for Wednesday and I'll have a better answer for you, right? For the weekend, nobody's dropped the class yet, so don't perfect that again. Oh, okay, so you're,
Yeah,
I'm sure,
Yeah,
you gotta do, let us worry about everybody on the wait list. I appreciate you thinking about it.
Oh, yeah, for sure.
It's unfortunate, but it's, you know, you, at a small school, there's pluses and minuses.
Yeah, for sure.
More attention, but less flexible.
Yeah, you're right.
I guess my question, if you have a minute, is also the wait list question.
Yeah. So there hasn't been any movement yet, I usually people will wait until this first week, they'll wait
Yeah.
until the deadline.
For sure.
So can't really answer it, I can tell you, if there's no movement, then I can't really let you in.
Mhm.
Just because with labs, it's a safety issue, can't go over cap, so. I'm hopeful there'll be some movement, there usually is, but there wasn't any over the weekend yet.
So,
And you're Jennifer, right? So I did add you as an observer, right? You should,
Yes.
Canvas should show up.
yes, except for I wasn't able to get into the assignment.
Right, so it won't let you submit anything because I can't add you as a student.
As well as there was some other assignment that I tried to open and it was.
Yeah, so for those
The quiz,
ones,
it
the
was
quiz,
quiz.
the
The
quiz,
question.
yeah.
I emailed you a question now.
Perfect, that's great. So was it about the course material, should I?
You already answered it. It was
Okay.
about algebra tutoring.
Cool, perfect. Yeah, so you'll be able to see the material, get access to the lectures and slides and everything. But you can't participate, you can't submit anything until you get added to as a full student. So that's,
I mean, if someone to be a side of
you could even click on it to open it.
right, that's what I'm saying.
Okay, then,
But yeah,
but I gave it to you, it's this one, right?
I had that,
You
yeah,
had that one.
perfect.
So just let me know and I'll
Okay.
print any of those ones off. That's good for me to know, because I didn't realize you couldn't even open the assignments.
Yes. that's right.
Good to know. Okay,
And then as far as, I guess I have wait lists, like position questions.
so I'm keeping track of them. All right, we'll go ahead and jump back in here. Just one thing I also point out is I always upload the slides as a PDF before class. It might only be a few minutes before class. But if a lot of people find it easier to either take notes, if you go to the library and get them printed beforehand, or if you just have your laptop open, so you're not frantically copying everything down. That's already on the slides, if you just go to week 2. So here's the PDF of the slides, you can save it. You can print it out, take notes directly on the slides then. But then it's just all the same information. However, since I'm usually just finishing my lecture prep, I'm right up until I come right up here, especially when I'm trying to incorporate as many questions as possible and answer everybody's concerns. Usually sometime between half an hour before class and 2 minutes before class, these slides will get uploaded. But they will be uploaded before class. If you don't see them before class, by the time class starts, just ask me about it and I can fix it during break. And then you can follow along that way if you like. All right. Let's jump back. And let's start talking about units. All right, so there's a couple of key aspects to any number that we use in sciences. Pretty much the only time you're ever gonna see a number that doesn't have a unit or some sort of context is gonna be in math. Those math folks, they're interesting. They like numbers with no units, with no meaning besides just actual numbers. In the sciences, we like to know what a number means. And the way that we know what a number means is by having a unit put to it. So if you look up what a unit is on, I don't remember if this was a Wikipedia definition or dictionary definition. It's definite magnitudes of physical qualities, which is kind of still a little bit abstract. Basically, The unit is what gives a number context. Units tell us what a number means. Without that, if I just say, hey, I've got 3. What do I have 3 of? Who knows, right? Now, there might be other contexts. You might say things like that in everyday language. If somebody says, how many pieces of pizza do you have for lunch? You can say, I have 3, because it's implied that I'm talking about pieces of pizza. If you said, how many pieces of pizza do you have? And I said, I have 3 grains of rice. That doesn't really make much sense, but at least grains of rice tells you what I'm talking about, right? So we're always gonna want units in the sciences. Because without units, we don't know what the context is. Another example, if you go to the gas station and pay in cash, you have to give a unit. Again, it might be implied from context. If I walked up to the gas station cashier and said, I need 20 on 5, it's implied that it's $20 on pump 5, right? But that's just because they're used to hearing that over and over again. If I wanted to pay in euros instead of dollars and I was in South Lake Tahoe, I probably would need to specify 20 euros. And then they're gonna look at me funny and tell me that they don't take euros. But that's beside the point. The point is that the units are what tell that cashier what I'm actually talking about. If you're administering medication or taking medication, you need units, right? If I said, I'm gonna take 5 grams of ibuprofen, that'd be a lot or a little? A lot, right? 1 tablet of ibuprofen of Advil is 200 milligrams. So 5 grams is 5,000 milligrams. So now we're looking at like 100 tablets, 100, no, 50 pills. That's a lot, that's too many pills. Don't do that. But also the medication is part of what determines what's a lot, right? If I said I'm taking 200 milligrams of ibuprofen, nobody bats an eye. If I said I'm taking 200 milligrams of LSD, see you in a couple months. Right, so units, not just the raw units, but also units of what wind up being important. So context is a really big deal when we're talking about this. So what are some basic units? Turns out there's lots of units for all sorts of stuff. What units do we use for length? What's another word for length, I guess, too? Miles. Meters. Miles is a weird one because we don't think about miles as being a length. Typically in everyday language, we'd say that's a distance, right? Is there any difference between distance and length? Not really. So miles, meters, anything else? What else can you come up with? Inches, feet, micrometers. Getting into some prefixes. We're going to use prefixes a lot in this class too. There's some other weird ones. Can anybody think of a weird length? When I say weird, I mean stuff that we don't use in everyday language. That's still a length unit. What?
Yards?
Yards. A league. Does anybody know what a league is? I think it used to be the distance that could be walked in an hour by a human. On average, I want to say it's like 3 miles or something like that, or it might be 20 miles. I don't remember. Fathoms is one I remember seeing in like books when I was a kid. I want to say like it's probably something in the Chronicles of Narnia. I think Voyage to the Dawn Treader, they talk about fathoms a whole lot. And I remember being a kid and like, what the heck is a fathom? Fathom is 6 feet. They use it for measuring depth of water for boats. What's that? Hands. What do you use hands for? Horses get measured in hands, and it's literally. I think it's 4 inches. It's this way.
Yeah.
4 inches is a hand, something like that. Yeah, we're not going to use any of those. Astronomy has some fun ones too. Light year. Light year's a distance. Turns out parsec is as well. Star Wars fans are usually, you do the Kessel run in under 12 parsecs. Parsec is a distance, not a time. It just sounds like a time because it's got seconds at the end of it. But a parsec is actually a distance. Astronomical unit, AU, is the distance from the Earth to the sun on average. So there's a lot of different units for length and distance that we use depending on what context, right? We're not going to do anything in hands in this class. Not that I'm not an equestrian fan, but just who needs that trouble? When we can just do everything in terms of meters and use metric prefixes. They're called metric prefixes, but really they're just you can use them with any type of unit. It doesn't have to be a metric unit. And so when I say the metric prefixes, let me pull up the conversion sheet for this class. We'll just go. So the prefixes on units use a little bit of a different order than normal. So this is your conversion sheet. Your conversion sheet has all the conversions you're going to need for the final exam, and a lot that you don't need for the final exam, as well as relevant equations. I'm going to give you all this. You don't need to memorize any of this. I would recommend using this when we start doing unit conversions and practicing with units. It's a good one to have. It should be all-purpose enough for this class that if you have this page printed out in a periodic table, that's all the information you need for any of the problems in this class. So it's a good study habit to be in. Whatever you're going to use on the test, practice using it when you're doing all your other assignments too, so that you know exactly where everything is on the sheet of paper. You're not getting into the test and having to figure out where the conversions are. And so these are the main conversions we're going to use, but the one that I wanted to focus on are these unit prefixes. Unit prefixes are basically a way to modify any unit that you want. I already mentioned milligrams. Somebody mentioned micrometers, there's nanometers, there's picoseconds, there's gigahertz. All of these prefixes are basically just get stuck onto the front of another unit as a way to make a new unit that's based on the existing unit. So when you say grams is great, but I don't want to necessarily, let's go back to the ibuprofen example. I say 200 milligrams. For whatever reason, people don't like thinking in decimals. 200 milligrams is the same thing as saying 0.2 grams. But if you tell people in everyday life, take 0.2 grams of Advil, they're going to look at you like you've got 5 heads, right? For whatever reason, humans like, and not for whatever reason, the way that our brains evolve, the way that consciousness and cognition in humans evolved, we work best with whole numbers. We don't work very well with decimals. We do okay with fractions as long as we're only talking about halves and thirds. Our brain doesn't really work in decimals. So for that reason, we wind up using these other prefixes to just say, so that we can say, instead of saying 0.2 grams, we can say 200 milligrams. Because 200 is friendlier for the human brain to think about than 0.2 is. Once you get used to it, then you know they're really the same thing, and you get used to thinking about it that way. You don't really see a difference, but it's kind of understandable in some ways. Here's a fun limitation of the human brain in numbers. Do you know that your brain cannot visually count more than 3 objects at a time? Your brain only processes numbers. Really whole numbers, but basically 1, 2, and 3. If I ask you to count something more than 3, what your brain does is it breaks it up into groups of 2 and 3. If I say how many students are sitting at these first 2 tables, you can look at them and say you can't see 4. You see 2 and 2, and your brain knows to put that together and make 4. Anytime you have a group of objects that you're trying to count, you can catch your brain doing this if you're paying attention. It's kind of interesting. That literally anytime you count, even on like counting the dots on a die. Why do you think 6 on a die is structured that way? It's 3 and 3. So that's one of the reasons why we use these prefixes, is because even though I can say I'm gonna run 1,000 meters and it means the same as a kilometer, my brain processes 1 kilometer as different, and I have an idea of what 1 kilometer is. If I said, how far is 300 yards? What does that look like? What do? You're trying to estimate that in your head. You turn it into 3 football fields. You turn it into something that's 1, 2, or 3. At least that it's a whole number that you can wrap your head around. It's weird. Turns out consciousness is weird. All right, so how does that apply to our equation sheet? Basically, these unit prefixes, this is the way it's going to be on the conversion sheet, and it's just a list of, here's the name, here's the abbreviation, and here's the multiplier, which is basically how much bigger or smaller are you making something. If I say a kilogram, I come over here and I say, okay, kilo. Kilo is 10 to the 3. What does that mean? It means that there's 1,000 grams makes 1 kilogram. Right, so this is a whole bunch of units all mixed together. You can put these in front of anything. We don't think about micro inches very often, but that's a real unit. You can put micro in front of any unit. A micro inch is a 1/1,000,000th of an inch. Usually we use meters instead of that because we think of these as being metric prefixes, but they apply to anything. All right, more practice with that later. Just more fun thinking about units. What do these numbers mean? What units do we use for weight? Pounds. Pounds and grams are our standards, right? We're not going to do much with pounds in this class. There's not a good conversion. There's an okay conversion, but it's not an exact conversion to go from grams to pounds, so we're just going to ignore pounds. For this class, pounds don't exist, which is tricky because I, like most of you probably, I'm going to make the assumption, since we're in the US, that most of you grew up thinking in pounds. Hopefully, you grew up thinking in kilograms, but it's not been my experience in teaching this class. I still think in pounds because that's how I learned how to think about weight. But in the lab, we're going to do everything in grams. Any other weird weight units? There's some other weird ones. In Northern England and in Scotland, they don't do things in kilograms or pounds. You ask somebody how much they weigh, they'll give you an answer in stone. I think stone is about 20 pounds. So you say something like 9.5 stone, something like that. Weird. We're gonna avoid that. Don't do that, please.
I think it's awesome.
It's cool. It's a holdover from older times for sure. And probably literally there was a stone that was, this is what a stone is. And they said, okay, how many of these stones that are this size does it take to balance something on? And it was probably used for livestock originally because nobody cared about their body weight back in the 1300s. Volume? Liters. Yeah, basically volume is dimension is length in 3 dimensions, right? So anything cubed could be a volume too. Any length unit could also be a volume unit. We use liters and milliliters mostly in this class, but cubic miles is a volume. Anytime you've got 3 length units multiplied together, that's like saying you've got a box that is 1 mile by 1 mile by 1 mile. It's a cubic mile. It's a big box. For context, I think Lake Tahoe is about 36 cubic miles. The entirety of Lake Tahoe going all the way down to the bottom. So a cubic mile is a big number. But we'll do some things in cubic centimeters and things like that too. You can kind of pick whatever volume you want for that too. You can meet ounces or liters or pints or quarts. Anybody know all the volume conversions? Any bakers? Usually it's people that bake that know a lot of the imperial unit volume conversions off the top of their head. How many teaspoons are in a tablespoon? This is just good knowledge for everyday life. Close. It's not so friendly though. It's 3. There's 3 teaspoons in a tablespoon, and I have no idea why.
Because our brain thinks in.
Because our brain thinks in 3s. There you go. But time, is there a weird time units? Or just regular ones?
Fortnite.
A fortnight. Fortnite is a weird one. Fortnite's just 2 weeks. No idea why they named a video game after it. Yeah, we're gonna stick to, this is one of the few places where the metric system and imperial units kind of agree. They use seconds. If you get really into astronomy, there's actually a slightly different definition of some of these time units. But yeah, seconds, minutes, hours, days, months, years, etc. In astronomy, there's a difference between, I want to say they call it a rotational day versus a sidereal day. Has to do with when you're rotating around. Are you rotating around until you rotate 360 degrees, or are you rotating around until the same point on Earth is pointed at the sun? A sidereal day is a little bit different because as the Earth rotates around the sun, it's actually not quite 360 degrees to get back to where the same point on Earth points towards the sun. Which is a little bit weird to think about because you have rotations within rotations when you start doing astronomy. We're gonna stick mostly to Earth-based units because technically every planet has its own day, right? We're just gonna call a day as exactly 24 hours. That simplifies things. Not exactly true, and it's definitely not true on other planets. You know who knows what planet has the shortest or the longest day? I want to say it's Venus. I just read a number about Venus's rotational day. It's something like 370 days, Earth days for Venus to make one rotation. So it actually finishes a year. Its day is longer than its year. Its year is something like 270 days, Earth days, but its day is 370 Earth days. Weird, huh? Are there other things that have units? What other numbers do you use on our everyday life?
Speed.
Yeah, computer science has a lot of its own units. Temperature is its own units, Fahrenheit versus Celsius. I have another one over here. Speed. Yeah, we're gonna get into combined units because really speed is 2 units combined together, right? It's a distance divided by a time. So combined units wind up showing up all over the place too. Any other fun ones you can think of? Light intensity, like lumens. Power, you got watts and things like that. There's energy is technically not the same as power. Turns out units get kind of complicated. We're going to start with the basic ones, and most of the other units come from these. There's some that are their own thing though. Frequency is a good example. Frequency is kind of like inverse time. Instead of how many seconds does it take for something to happen, it's how many times does it happen per second. So it's kind of a combined unit, but it's kind of its own thing. That's actually what hertz is. Gigahertz is a frequency unit. So what's that?
Bitterness.
Bitterness in beer. Yeah, IBUs. Stands for International Bitterness Units. They just didn't have a better name for it, so they called it a bitterness unit. It's basically how bitter is it. That's actually seems like it's subjective, but they actually have an objective way to measure that by looking at absorbance at a certain wavelength in the finished beer product. and then converting that of how much light gets absorbed in that wavelength and turning that into IBUs. Because when you start getting into the nitty gritty on beer, if you take alpha acids out of hops and you isomerize them into iso alpha acids, then they turn into IBUs and they don't have really any flavor beyond just bitter. And if you measure those iso alpha acids, and what their concentration is, you can convert that into IBUs. That's what IBUs is based on. We're basically going to stick to metric units in this class though. So meters, seconds, grams, liters, Celsius. We'll spend some time talking about temperature in a little bit, but for the most part, we're going to ignore imperial units other than the most basic ones like distance, just because we can't get around distance and pounds being something that show up every day here in the US. Yeah, I think that's all we looked up. If you look up the Wikipedia page for SI units, it's actually many more types of quantities or qualities that you're measuring, but most of them are some combination of these, other than things like lumens. All right, so how do we measure these things then? I say it's about a mile versus it's a mile, or if it's 1.5 miles versus it's 1 or 2 miles. How do we decide how many decimals we get to write down? That's going to be the rest of this class, basically, is figuring out how many numbers we get to write down. Riveting stuff. But if we get this down well, it's going to serve you well when it comes to learning how to round numbers properly when we do calculations. So for starters, how do we know if a number is approximate or not? If I say it's a mile to my house, is that an exact number? I mean, you don't know where my house is, but odds are it's not literally exactly a mile from where I'm standing right now, right? And even if it was, now it's not. So how do I know if I say it's a mile from now, how do I know how precise that number is? And how do I know if it's what's called a measured number? So measured number is anything where if you added more decimal points to it, it would get more exact. So basically a measured number is always approximate. There is no such thing as an exact measured number, because there's always some level of judgment or some level of rounding or approximation that's going on. And so what's the opposite of a measured number then? Any thoughts?
Estimated, I guess.
Oh, so measured is estimated in a lot of ways.
Yes.
A what?
Yes.
Guess? No, because those are all, even if you're making a guess, that is a measurement. Right? You're using some amount of judgment. You might not have a scale like this to put up, but it's still a measured number. You're just measuring using your eyes. So an exact number. The opposite of a measured number is an exact number. An exact number is something where no matter how many decimal points you add, you're not going to make it more accurate. In other words, it's something where it is 100% that number. So can anybody think of a definition of an exact number? Or sorry, an example of an exact number?
Base of a unit, like 0 Kelvin.
So base of a unit. So that's what we call it, a definition. And so definitions typically are exact. So if I say there's 12 inches in a foot, is it about 12 inches in a foot? No, it's exactly 12 inches in a foot. It's not 12.1 sometimes and 12.0 other times. It's 12. It's 12.000 out to infinity. So that if it's a definition, it's an exact number. So anytime you've got a definition. There's one other case where exact numbers show up. How many markers do I have? Is it about 3? Exactly 3. If you're counting discrete objects, that's usually an exact number too. Right? Because it's not 3.2 markers, it's 3 markers. There's no possible way I could be off by a marker. Especially if there's only 3 of them, right? Where might that fall apart though? If we're counting discrete objects like people. Anybody think of an example of when the number of people is not an exact number? Population?
Yeah, I was just saying population and what people define as people is for a while, it's.
Well, that's more on the politics side than anything else, but yeah, if we, let's leave that one part out of it. Yeah, when we get to large numbers of people, we still have to approximate that, right? So if we said that, you know, how many people were at the Night Monsters game last Friday? I don't know, but if I was there, I could get a decent approximation. It might be off by a person though, I might have counted wrong. So when you get to large enough numbers where you might count wrong, then then it is still an approximation. Like, trying to think. When Oracle Park sells out, it's something like 28,322 people attended a Giants game. Is it actually that many people? Probably not. They might say that there's that many people there, but there's probably not actually that many people there, so it's not an exact number. So measured numbers involve some approximation, and most numbers we're going to deal with are going to be measured numbers. We don't have microscopes good enough that we could actually count individual atoms, and even if we did, we'd be getting into that realm of there's just too many, I might have counted wrong. So in chemistry, since we're going to deal with atoms and things like that, we're going to, almost all of the numbers we're going to deal with are going to be approximate. So when we measure a number, we have a procedure for it. If I said how, the keyboard stopped working for a second. If I said look at A, how many centimeters is this piece of wood? 4.5? Between 4 and 5 for sure, right? Everybody can agree that this is definitely between 4 and 5. So why not just say it's 4?
Because it's not all the way to 4.
It's not right at 4. We're using judgment to decide, well, it's not right at 4. What about this one? What about C? But we used the same ruler. This one we said we estimated one spot further than that, right? So basically the rules for measuring things are going to be based on what object are we using to measure and where is the uncertainty. Could we be off by an entire centimeter for A or for B? Sorry, A or for C? No, there's no uncertainty associated with the ones place. There is some uncertainty associated with the tens place though, right? Said 4.5, but could it be a little bit more than a half? Could it be 4.6? Depending on where you're standing in the room, it might even look like 4.4. Depending on your eyes when you're measuring it yourself. So the uncertainty is basically how far off could your measurement be? We know it's 4 point something. And then we're going to estimate one spot past, one decimal place past where we're certain. So I would look at that and I would say, yeah, that does look like it's right about in the middle. So I would say 4.5 centimeters. but that tenths place has uncertainty with it. If I'm looking at it and I say, well, from standing on this side, it looks really close to 4.5, but not exactly 4.5. So I'm gonna say 4.52. Now I've estimated 2 decimal places, right? Am I actually certain about that 5 in the tenths place? Basically, when we measure numbers in the sciences, we always assume the last digit in your number is where the uncertainty is. So by writing 4.52, I'm saying I am certain about the 4, I'm certain about the 5, and I'm guessing on the 2. That's not what A actually looks like though, right? We don't want to say 4.52 for A, even if it doesn't look like it's really 4.5. Even if it looks like it's a little bit more than 4.5, we're not allowed to go more than 1 decimal place past our last markings. Specifically our last decimal markings. So, and I'll define that again in a second. So I wouldn't say 4.52. I would just say 4.5. What about for C? It looks like it's right on the line for 3, right? Could I be off? But if I write just 3, that's implying I could be off by an entire centimeter. Is there any way I'm off by an entire centimeter? What do? 3.0. We're still estimating that tenths place. And the way we say the tenths place is what I'm estimating is we write the 0.0, even if it's not going to affect our calculations. We plug 3.0 into our calculator just says, oh, you mean 3? Well, in the sciences, that 3.0 is important, even if it's not going to change the calculation, because that's how you communicate to the reader where the uncertainty is. I might be off a little bit. Again, standing from way over at this angle, I would say maybe it's maybe a little bit more than 3. But it's definitely not like a whole tenth over that. So 3.0 is probably my best guess, but I might be off by 0.1 centimeters. Right, so anytime you measure a number, you think a scale like this, you're always gonna you're gonna estimate 1 spot past where you're certain. If I'm certain about the ones place, I estimate the tenths. Now, that actually means that how many digits we get to use depends on our ruler in this case, right? A and B, it's the same object, actually. It's the same piece of wood. But when you get a better ruler, we can see it's definitely closer to 4.6 than it is to 4.5, right? By having a better ruler, we get to estimate more. So we might look at this and say, well, I'm definitely sure about the ones place. And I'm definitely sure it's between 4.5 and 4.6. So I'm certain about the tenths place. Sorry, should be a 5. It's 4.5 something. And then we use our judgment. And then we estimate that last spot, which, depending on where you're sitting and how small the object actually is, has anybody actually tried to estimate 1/10 of a millimeter before using one of those crappy wooden rulers that you got in high school or middle school? It's really, really hard. A millimeter is like that, right? Trying to estimate 1/10 of a millimeter is tricky. Even when it's blown up like this, it's still hard to see. That's why there's this uncertainty with that estimation. I'm gonna look at this personally and I'd say, okay, well, it's definitely more than halfway between 4.5 and 4.6. So I'm gonna say 4.57. Your number might be different than mine. That's okay. Everybody's gonna look at that and say it's 4.5 something. And then we're estimating that last spot. Every number, every measured number that you'll see anywhere is always estimating that last digit that's reported. And that applies to technology too. If technology is properly programmed, it should follow those same rules. So if you look at your Apple Watch and it says you went for a run that was 4.2 miles, that's assuming that it might be off by a tenth of a mile. If it says 4.21, it's saying it might be off by a tenth of a mile, or sorry, a hundredth of a mile. And the trouble is that both calculators and other and computer science programs, apps, they report all the way out to however many digits can fit on the screen sometimes, right? If they're not programmed properly. So you can't necessarily trust it outside of the lab unless you know what that particular device and how the apps were set up. Because if I go for a run and my Apple Watch says 4.21753 miles, that seems like overkill, right? Does anybody believe that Apple is actually measuring that accurately, how long my run was? No. I believe it maybe to the thousandth of a mile. Thousandth of a mile, we're talking about plus or minus 5 feet. It might be that accurate, depending on where you are, where satellites are, reception, that kind of thing. It's definitely not can't trust those numbers at all, but the calculator will still give them to you. So this is why we need to learn the rules for how do we decide where to round as well. Because we're not ever, thinking this class, I don't like to use absolutes. Very rarely in this class are we ever going to measure a number and that's that in this class. Almost always when we measure a number, we're going to take it and then do math with it. So we need to know how to decide where to round, so that when we get this number from our calculator, we know where to round it appropriately. A note about types of scales. Most common scales in everyday life are what are called fractional scales, which they're named that because they're made up of fractions. So if we had a tape measure, said 3 inches, 4 inches, there's 3.5, there's a quarter, there's an eighth. Fractional scales get really hard to figure out how to actually decide where these to round and what to do with these numbers, right? Especially considering our calculators work best in terms of decimals. We don't want to use fractional scales. Basically, if it's a fractional scale, we're going to pretend those fraction numbers aren't even there. We're just going to treat this like it's 3 inches and 4 inches. We're estimating the tenths place. If it's a decimal scale, that means that there's 10 marking, well, there's 9 markings. There's 10 divisions in between each of these. So if I had an object that went that far, using this decimal or this fractional scale, you can use the fractional scale to kind of help you. I know it's definitely more than 3.5 and less than 3 3/4. But if we want to report a decimal number there, we're still going to be estimating the tenths place. We're going to ignore all of that. And just say it's 3.6 or 3.7, depending on what your eyes see. If it's a decimal scale, we can be very certain that this object is between 3.6 and 3.7. Our uncertainty now is in the hundredths place again. So decimal scales are what we want. If it's not a decimal scale, you can't trust it. If it's not a decimal scale, it is an estimation for this class. Turns out there's rules for how you do this with fractional scales too, but then it basically gets really, really complicated and a pain, and since I want you to only use decimals in this class anyway, we're gonna pretend fractional scales don't exist. If you go into engineering in the US and you're stuck using imperial units, you can still get tape measures and rulers that do inches in decimal scales that are where you have 10 markings, so you can actually write down 3.21 inches. That's just not what you find at the hardware store. Most things you find at the hardware store are gonna be fractional scales. All right, so questions about the difference between fractional and decimal? Here's the slide. I already covered this stuff, but this is just the procedure for how you measure things. You write down the most accurate number you know with absolute certainty, and then you estimate one more decimal place. All right? So we already did these 3 examples, but 4.5 centimeters. 4.56 centimeters. 3.0 centimeters. Let's do some new practices. Here are my examples. And leave those off, really? All right. So we have more examples that we'll do at the beginning of class on Wednesday. Last concept then for this class. How do we know how precise a number is? We know how precise a number is based on how many digits are measured. Those are what we call significant digits. Okay, so first off, what's the difference between accurate and precise? Or is there a difference?
You can have a precise measurement that's completely wrong, 3.57.
Yeah, so precision has to do with how many digits got measured. Accuracy is how close you are to the real number. Right, so I always use a dartboard as an example. Or an archery target. If I'm shooting arrows in an archery target and I shoot 3 arrows and I land them all close together, but not close to the target, to the bullseye, that's precise, but it's not accurate. If I take 3 shots and I land here and here and here, that's not precise. But if I average all of them out, it kind of averages out to the bullseye, doesn't it? That's accurate without being precise. Ideally, in the sciences, we want both. We want precision and accuracy. That's not always possible. And understanding the difference between those two is kind of an important concept. In general, we prefer accuracy over precision if we have to choose between these. Because if we take enough data points, let's say we added a whole bunch more. That's about 10. If they're all really precise and I average all these out, it's gonna be somewhere right there, right? It's not all that close to the real number. If I have a large number of measurements, even if they're not precise, a large enough number, I can still take an average. Well, there's probably gonna be some that are closer than others. But a large enough number of data points can overcome a lack of precision. There's no way to overcome a lack of accuracy. If you're precise without being accurate, you're always going to be off, no matter what. But if you're accurate without precision, you just need to keep going. take more and more and more and more data points, and eventually you're gonna get something that averages out to the real value. Or close to the real value. Close to the bullseye, as an analogy. So. If we know that precision, we still wanna be precise. Ideally, the ideal case is we're both of these. We're precise and we're accurate. I don't know if anybody's ever watched archery and pistol shooting and things like that at the Olympics. But they are both precise and accurate. That's the gold standard. That's what we're going for. So then how do we know how precise our numbers are? If we don't have something visual like this. Well, for the most part, we look at how many digits got measured, how many significant digits we have. So I was taught to call them significant figures. More modern textbooks call them significant digits. They mean the same thing. I'm probably going to call them significant figures because that's what I've been doing for the last however many years. But they mean the same thing, right? So, and when this is going to be the most common thing that you get marked down on this entire term. This is the most common thing that people lose points on. Luckily, it's usually like a quarter of a point. If I'm not specifically asking you about sig figs, then I'm pretty lenient with it. The whole point is you want to communicate to your reader how good your number is. And so, counting significant figures. A number is a significant number if it's measured. The easiest way to tell if it's measured or not is if it's non-zero. If a number is non-zero, you can assume it was measured. Because otherwise, why would you write it down? And so, if I said 5.13 centimeters, all three digits were measured. We're certain about the 5. Assuming that whoever wrote this down is following the rules. We're certain about 5, we're certain about the 1, we're uncertain in the hundredths place. But all three of those digits were measured. So they're all three significant digits. We abbreviate sig figs, significant figures, as sig figs or SF in a lot of cases. Like I said, we'll mark you down a lot for this, so I'm not going to write significant digits every single time. It's just gonna be SF usually. If it's a 0 at the end of a decimal, like 5.310, the only reason to write that 0 is if it was measured. Right? We're not writing it there because it's gonna affect our calculation. And we're not writing it there because we need it there to tell us where the decimal point goes. We're only writing it there because it was measured. If it's a digit that's a 0 between two non-zero digits, well, that had to get measured too. If I measured the 5 and I measured the 4, I had to measure the 0 too. Makes sense, right? So in terms of these numbers, sometimes it's easier to think about what's not a significant digit. And that's going to be any leading zeros. There's an infinite number of zeros to the left of that 5, right? Are those measured? No. They don't count. They're not doing anything. We don't measure that. If this table is 6 feet long, I'm not going to say there are 0 tens in this number. I'm going to start with the ones because that's where we're measuring, the decimal place we're measuring. And that also applies if it's behind the decimal point. These are still not measured. Just like this 0 is not measured, these ones are not measured either. So they're not sig figs either. This is still 2 sig figs. These count. Those don't. Okay? Then last but not least, the foolproof way, where you don't even have to think about it, is if it's in the coefficient of scientific notation. If I say 5.0 times 10 to the 5 centimeters, Those are both sig figs. All right, so why does this matter? Because counting the number of sig figs and knowing where the uncertainty is going to tell us what to do when we start doing math with these numbers. It's so, for instance, if I had a box that was 2.0 centimeters tall and I don't know, 3.7 centimeters across. When you plug that into your calculator, let me make this more interesting. Let's call that 5.7. When you want to find the area of that box, what's the formula for area of a box? Base times height, length times width. So 2 times 5.7. When you plug that into your calculator, you're then going to get 11.4 centimeters squared. I think if I did my math right in my head. But if we could be off by an entire tenth here, we could be off by an entire tenth here. Doesn't our uncertainty compound then? Can we actually be sure we're only off by a tenth here if each of our starting numbers could be off by an entire tenth? No, it turns out when we multiply things, we have to round based on how many sig figs were in the numbers we started with. 2.0 has 2 sig figs. 5.7 has 2 sig figs. Our answer can only have 2 sig figs. So it would just be 11. Because if we could be off by an entire tenth here and off by an entire tenth here, when we multiply them, we could be off by an entire 1, potentially. Because the uncertainties compound as well. So when we multiply and when we divide, we have to look at how many sig figs we started with. You keep the same number of sig figs as your least precise number. So let's say that this is 11.7 centimeters and still keep it easy for me to do in my head. How many sig figs are here? 3. How many sig figs do I get to keep?
2.
Just the 2. Whatever your lowest number of sig figs, that's your least precise measurement. So that's the one that controls how many sig figs you get to keep at the end. Think about if it's 2.0, being off by a tenth is 5% of your entire number. If your entire number, you could be off by 5%, that's going to dictate how accurate your answer is. If I'm off by a tenth here, again, the math's not as easy in my head, but it's going to be something like 1%. If I'm off by a tenth of a centimeter here. 11.8 versus 11.7 versus 11.6. That's a lot smaller swing in terms of precision, right? Versus 1.9 versus 2.0, that's kind of a big deal as far as what percent of your starting number. So whatever your least precise number is dictates your final number of sig figs. Make sense? Right, so when we do math, when we do multiplication and division, number of sig figs is what's going to matter most. What about addition? If I say, I'm gonna drive from here to Sacramento to the state building, and it's 99.7 miles. Where's the uncertainty? In the 0.7, right? So 99.7 miles. that could be off by 0.1 miles. Then I say, okay, I get out of my car at the Capitol and I walk 32 feet. How far off is that measurement? How, or what's the uncertainty if I say 32 feet? Plus or minus 1 foot. Is 1 foot more or less than 1/10 of a mile? A lot less. 1/10 of a mile is like 500 feet, right? There's 5,000 feet in a mile, so 1/10 of a mile is about 500 feet. If I wanted to add these two distances together, how far off could my answer be? I could still be plus or minus a mile here, right? It doesn't matter how good this 32 feet measurement is if I could be off by 1/10 of a mile. When we're adding and subtracting numbers, whatever has the highest uncertainty changes where we round. Here's another example. I use driving as a good example here. If your friend is driving up here from the Bay Area and it's gonna take 4 hours and 15 minutes. Let's make it a little bit even more interesting. 4 hours, 4.16 hours is what Google Maps says. And then they call you at Placerville and said, oh man, the light just turned red. I'm gonna be 15 seconds late. That's silly, right? Because where is the uncertainty? The uncertainty is already here. 15 seconds is less than the uncertainty we already have. We can make it even more realistic. If we say it's gonna take them 4.5 hours, plus or minus 10 minutes already. Adding 15 seconds to that is not really gonna change the estimate, is it? Let's see, 4 hours, 4.5 hours. Plus, what's 15 seconds as a fraction of an hour? That's a fraction of a minute, that's a fourth of a minute, and then divide that by 60 again. They're like 0.0015 hours. Is that actually gonna change anything? It's already within the existing uncertainty. So when we add and subtract numbers, we keep the same uncertainty as our starting numbers, with our least certain number. So addition and subtraction is all about where's the uncertainty. Multiplication and division is all about where are the sig figs. All right, and it kind of makes sense a little bit. The way that I always remembered is addition and subtraction is the rule that makes sense. And multiplication and division is the easier one. Because counting sig figs is a lot easier sometimes than figuring out where the uncertainty is. But it's really easy to just look at sig figs and say, oh, 2 sig figs, 4 sig figs, I'm keeping 2. Right, so this is gonna be our rules for rounding. Anytime you do math with a measured number, it's either gonna come back to where's the uncertainty or where's the precision? How many decimal points do I get to keep? How many sig figs do I get to keep? All right? All right, I know that was a kind of a dry lecture. We'll make them more fun going forward. We gotta get the boring stuff out of the way though. Len, we'll end a couple minutes early. Lab, if you have lab today, is at 1:30. If you're on the wait list for today's lab section, go ahead and come to lab anyway. Okay, show of hands though, real quick. Who's still on the wait list? Do I really just have, I think I have my 3. There's waitlisted. Okay. Everybody else is not here. Cool. All right. I'll see half of you at 1:30. Everybody else on Wednesday.
Oh, I.